Good evening, everyone. It's a pleasure to welcome you here to this, for me, really exciting event. My name is Johannes Henn. I'm a director at the Max-Planck-Institut for Physics in Munich. So this evening we have a pleasure of hearing first a talk with the mysterious title, The End of Space-Time. Then there'll be refreshments at a reception just outside. And then in the second part, we'll have a moderated discussion, which involves various people. So there's Nima Arkani-Hamed, a theoretical physicist from Princeton. There's Professor Nima. There's Professor Armin Nasseh here from LMU Munich. And the discussion will be moderated by Jan Rubner, who is Vice President of Communication at TUM University. So this event is part of a workshop that's organized through the Cluster of Excellence, Origins, which is shared between LMU University, TUM University, and the Max-Planck-Institut for Physics, among other institutions. And it's a pleasure to see many colleagues from these institutions here, among others Managing Director Dieter Lüst of the Max-Planck-Institut of Physics, and many other colleagues. I'd like to say a special thanks to the many people who helped organizing, making possible this event. There's a lot of them, so let me just mention in particular Barbara Wankerl, who's head of communication at Max Planck, and her colleague Sorana Scholtes, and also our secretary Vera Kudrin, without whom, three of them, I think it's fair to say this event would not have taken place. So I think it's worthwhile to give a big hand of applause to the three of them. I'd also like to say welcome to people who are following this event online. I see we have a full house here, so it's also being streamed through the Max Planck the Institute's YouTube channel, and I think also through the Institute for Advanced Studies channel at Princeton. So whoever's online, also welcome to all of you. So now, without further ado, I'd like to just briefly introduce the speaker. So Nima is a theoretical physicist from Princeton, as I said, works at the Institute for Advanced Study. His work is trying to connect theory and experiment, and I think he's particularly interested in different experiments ranging from collisions of particles, of elementary particles like at the LHC at CERN, but also at the same time ranging to experiments to do with cosmological observations. So that's really a broad span of different kinds of physics. So I'm very excited now to hand over to Nima and to hear about the end of space-time. There'll be a 30-minute talk. After the talk, there'll also be a chance to ask questions to Nima. So let's have a big hand of applause for Nima.
All right, is this thing on? Am I too loud? Is it okay? All right, very good. Okay, well, it's really a fantastic pleasure to be here. And indeed, I'm talking about the sort of a rather dramatic sounding title about the end of space-time. But it's not really hyperbole. We are at a point in the development of fundamental physics. I think a lot of people feel, which is the kind of thing that happens on the sort of once-a-century timescale in this business, where the fundamental principles that by now we're spectacularly successful at describing everything we see in the real world, from the tiniest distances we're probing at accelerators like the Large Hadron Collider, 1,000 times smaller than the nucleus of the atom, all the way out to the size of the observable universe, 10, 15 billion light years across. There's a set of ideas and principles that were handed to us by the revolutions in the first part of the 20th century, which were these revolutionary developments of the principles of space-time and of quantum mechanics, both of which, of course, have huge contributions from German physics and physicists. And these twin principles turn out to be astonishingly restrictive in how they allow us to talk about consistent laws of nature on the one hand, and astonishingly powerful on the other. And it's indeed essentially these principles and not much else that, that goes into giving us a menu of possibilities for what the world could possibly look like, and a particular combination, the sort of theoretical framework that lots of talk about, laws of physics that are compatible with quantum mechanics, the principles of quantum mechanics in space-time is known as quantum field theory. So that's a sort of a large theoretical framework that lets us talk about possible laws of physics. And there's a particular quantum field theory. It's a famous standard model of particle physics and cosmology that describes everything we see in the world around us over the huge range of distances that we just talked about. So we're in a situation where our existing principles tended to from these revolutions are astonishingly powerful, and they work, but we have strong suspicions that the next step in physics has got to pull the rug out from under us and has to remove some of these principles from their primary role in the description of physics. And maybe this statement is a statement which most theoretical physicists who have thought about this problem would agree with, that certainly the notion of space-time is likely an approximate one and won't survive in a more the next complete description of physics. And this is because of some very simple thought experiments that we can do that have to do with the presence of both gravity and quantum mechanics. So the slogan is that because of gravity and quantum mechanics, the notion of space-time is doomed. So why is that? So let's imagine doing a few simple thought experiments. So I'm a terrible artist, so you're going to have to tolerate my terrible art in this talk. This is supposed to be a magnifying glass, okay? But let's say I'm going to use this magnifying glass to try to look at some small region of space and time, just to see what's there, just in the vacuum. Now, because of quantum mechanics and Heisenberg's uncertainty principle, in order to look at shorter and shorter distances, literally to look, I'd have to look at it with light with shorter and shorter wavelengths. That would have higher and higher frequencies. And in quantum mechanics, that would tell us that the minimum energy that I would need to probe very short distances has got to actually get larger and larger. So in order to probe shorter and shorter distances, we need to put more and more energy into a smaller and smaller region of space. That's the explanation for the huge irony why gigantic particle accelerators like the Large Hadron Collider, which are 27 kilometers around, are what we have to use to study nature at the tiniest distances we've ever probed. We need the biggest machine to probe the tiniest distances ever, precisely because of this business about the uncertainty principle. But anyway, in a world without gravity and infinite funds, you just ask governments for more and more and more money, and you can probe arbitrarily short distances by going to arbitrarily high energies. But in the actual world, we have gravity, and something very bad happens at some point. You put so much energy into such a tiny region of space that Einstein tells us that E equals mc squared. So it's like putting an enormous amount of mass into a tiny region of space. And you know what happens when you put a huge amount of mass into a tiny region of space? You collapse the region you're looking at into a black hole, and no information can possibly get out of it. So your act of trying to look at very tiny distances instead produces a black hole that makes it impossible to see what's going on in there. And if you try to do this with an even more powerful microscope, an even higher energies, what happens? You make an even larger black hole. So your attempt to probe shorter and shorter distances stymies itself, and it's simply impossible to give operational meaning to distances and times that are small enough. Now, the relevant distances and times involved here are tiny, 10 to the minus 33 centimeters, times of order 10 to the minus 43 seconds. That's how long it takes light to traverse a distance of 10 to the minus 33 centimeters. The fact that, just to compare, the size of the atom is 10 to the minus 8 centimeters. The size that we're probing at the Large Hadron Collider is 10 to the minus 17 centimeters. So we're a long, long way from probing this directly experimentally. Nonetheless, we can do this thought experiment, and we see that something new has to happen. And every time it's happened to us before in physics that we can't even in principle give operational meaning to some concept, in this case we're trying to give operational meaning to space and time, it's not that that concept doesn't actually exist. And in the more complete definition of physics, it won't be there. And somehow it will arise as an approximate emergent phenomenon from more primitive building blocks. Now, where do these questions become important? Well, there's a few obvious places where this kind of question becomes important. For example, we know the universe is expanding, so if we run the picture of the expanding universe back in time, it's contracting, getting hotter and hotter, denser and denser. And there's the moment that we colloquially refer to as the Big Bang, where the curvatures are of the universe and the temperatures and everything is at this ridiculous scale we're just talking about on the previous slide. Now, sometimes people ask what happened at the Big Bang or before the Big Bang, and we don't know, because what's going on is that the whole notion of before is breaking down. The whole notion of time is breaking down around the Big Bang. So it's not even clear if the words make sense, what happened before. Similar things happen if you throw yourself into a black hole. If you cross the event horizon of a black hole, then what happens inside isn't like you hit a point that's sitting there, but it's like being on the inside of a collapsing universe, and it's like running this picture of the expanding universe in reverse, and you get sort of crunched in your future at some point. Again, we don't know what happens there. So these are just places where our theories simply break down. There are well-posed questions that we can't give answers to, and they break down when quantum mechanics and gravity both become dominantly strong. Now, there's been a lot of work over the past 30, 40 years thinking about this problem from various points of view. One of the remarkable developments that would be a whole series of colloquia on its own that I won't say anything about in detail today, but just to show you the sort of unity of concepts and ideas in physics, is that around a little over 20 years ago, string theorists realized that we could think about this idea of space-time emerging from more primitive building blocks, at least in a first toy setting, where you can see that space can emerge from building blocks that don't have space in it. And physicists love to put systems in boxes. And so what you want to do, if you're studying this kind of fundamental question, is consider a whole universe in a box. And there's a way to talk about a universe in a box where the inside of the box is a very curved space. So you can really think of this as a tin can, the way it looks like in this picture. But the geometry on the inside of the tin can is curved in an unusual way, so that the distance from any point on the inside to the walls of the tin can is infinite, but it takes light a finite amount of time to bounce off the walls. So this kind of unusual geometry is known as anti-de Sitter space. And physicists realized that if they could imagine experiments that were done on beginning and ending on the walls of the space, just pinging the walls of the box, then you would imagine what's going on. You ping the walls, some waves come crashing in, they go crashing back out, you measure what happens out as a function of what you threw in. But they realized that they could give a description of what happened here without ever mentioning the existence of the interior, only talking about ordinary interactions of particles that live on the walls of this box. And in a very concrete sense, the inside of the box kind of emerges out of the dynamics of thinking about the very strong interactions of particles that only live on the walls of the box. When the interactions between these particles are very strong and you can't follow what each one of them is doing individually, there's an effective description of what's going on that makes it look as if there's an interior, with space in the interior, gravity in the interior, even strings in the interior. But fundamentally, there's just sort of particles interacting very, very strongly on the walls. So this is a first example where out of a quantum mechanical system with very, very strong interactions with particles emerges space and gravity in the interior. And there's the whole general idea is known as holography. It's something like the colloquial picture of a hologram, which is a fundamentally two-dimensional thing, but which encodes three-dimensional information. And there's many aspects of this dictionary. I'll just mention one of them, one of the most basic ones. If someone told you, look, this interior space here really doesn't exist, everything is sort of living on a screen out there, you would say, what the heck are you talking about? I could have this purple ball and the green ball, and one of them is here and the other one's further out. So what could it possibly mean that they're in different positions here if this space isn't really there? And the answer is that the purple dot in this description is described by some kind of fuzz of energy of some size in the wall description. And as you move the purple dot to the green dot, that corresponds to changing the size of the ball. So somehow the position in this extra space is encoded by the size of excitations in this hologram. So that just gives you some idea how the information, which is sort of lower dimensional, can encode in it properties that we ascribe to the presence of space, and when you study it further, gravity and lots of other things coming out as well. Okay, so this is a huge subject that's being studied intensively, continues to be studied intensively. But the world in a tin can is not our world. Okay, we don't live in a tin can. Very important about this tin can is that it's infinitely old. It's a tin can that lived forever. It will live forever into the future. And most of the interesting questions about our universe, most of the literally existential questions about our universe are cosmological ones. They have to do with the fact that our universe was born at some point. We'd like to know how our universe was born, what it means that our universe was born. We want to know something about the fate of the universe in the future. All of these questions involve the notion of time in a crucial way. And I probably don't have time to talk about this in a detail, but there are some questions about the birth of the universe at the Big Bang that are mysterious. There is a whole Pandora's box of questions that perhaps in a question session I'll say something more about if people ask, about something that astronomers discovered in the late 1990s, that the universe is not only expanding, but the rate at which it's expanding is accelerating. It's doubling in size at a constant rate every 10 billion years or so. And this fact that the universe is accelerating opens a huge number of conceptual mysteries on us in physics. And all of these ideas, both the notion of time plays a really crucial role, and for a variety of reasons, it looks like, especially if the notion of time goes away, somehow a lot has to change about our understanding in physics, but especially the things that are crucially tied into our descriptions of quantum mechanics also have to be modified in some way. So that's kind of a clue from far in the future that we have to eventually understand the emergence of time, and very likely not just the emergence of space-time, but very plausibly some kind of deeper rubric out of which both space-time and quantum mechanics emerge. So we were led to ask this question then: is there some deeper structure underlying space-time and quantum mechanics? And if so, it's clear that it must involve new physical and mathematical ideas. We can take some inspiration for what this might look like. So I hope it's clear this is a huge challenge. Okay? We're trying to understand what replaces space-time, maybe even what extends our notions of quantum mechanics. This is one of those questions that it sounds like a fascinating question to sort of think about, but not to get up in the morning and work on. And one of the, I think, most remarkable things about the period in the development of our field that we're in is that we're essentially at a point that you can get up in the morning and work on problems like this, or at least work on problems that are heading in this direction. There's many strategies for attacking these problems, but the one that I want to focus on for the rest of this talk, and the one that's most closely connected to the themes of this wonderful workshop that's being run here, has to do with this sort of, take some inspiration from this historical fact. That in the past, when similarly huge conceptual leaps were needed, and we did have a similar conceptual leap that was needed when we transitioned from the Newtonian classical universe to the discovery of quantum mechanics and the principles of space-time, quantum mechanics even more revolutionary. There were clues to what was coming that were hiding in plain sight as funny features of the existing theoretical framework. Again, I'll be happy to give some historical examples of that if people ask later, but I want to just move to at least some of the funny features of the existing theoretical framework that seem to be related to the question of what replaces the notion of space-time. So let's talk about, from all of these highfalutin, airy-fairy philosophical discussion to something very concrete and directly relevant to observations. In physics, we talk about the collisions of particles like protons at the Large Hadron Collider. When the protons collide, protons are big, messy bags of, they're not elementary particles themselves, they're big, messy bags. Well, not big, they're 10 to the minus 14 centimeters, but that's big on the scale that we're talking about here. Okay, so the messy bags of particles, they're made out of these really point-like elementary constituents, the quarks that are held together with gluons. So really what happens when these two protons collide at ridiculously high energies is that we care about the sort of head-on collisions between the quarks and the gluons, the elementary constituents that are inside the proton. And so we want to figure out what happens when the gluons hit each other, when the quarks and the gluons hit each other, quarks and quarks hit each other, and so on. Okay? So there's this big mess of stuff that's happening with these elementary particles smashing into each other. And for example, you need to be able to calculate what happens when 2 of the gluons and the proton hit each other, and 2 gluons come out, 3 gluons come out, 4 gluons come out. These are just ordinary processes that are happening tens of thousands or hundreds of thousands of times a second, depending on what exactly you're talking about. And this is just the known stuff, the standard stuff. So you have to be able to calculate this ordinary stuff that's going on, and accurately enough to subtract it and look for something new, right? So there's a motivation for just trying to understand how to do these bread and butter, ordinary seeming calculations. This does not seem to be the glamour part of theoretical physics. Okay, so this looks like an engineering problem, with apologies to any engineers in the audience. Okay, it looks like a complicated problem, and in fact, if you look at it, it's definitely complicated looking. Richard Feynman, one of the things that made him famous is he taught us how to think about these processes in the late 1940s, so 67 years ago, by imagining that here are the pictures of all the possible ways 2 gluons can come in and hit each other in various ways and turn into 4 gluons going out. And there's some basic interactions that can happen, these little sort of stick blobs with 4 things and 3 things meeting at a vertex. And there are some rules that you're supposed to, mathematical rules you're supposed to associate to each one of these pictures, but each one of them is supposed to represent some particular way that the process could happen in space-time, and you're supposed to add up all the different ways that the process could happen because of Feynman's way of thinking about quantum mechanics. Feynman taught us to think that quantum mechanics arises by thinking that particles take every conceivable path from one point to the other, and you're supposed to imagine adding up all the possible histories that something could happen in order to get the so-called quantum mechanical amplitude for a process. Maybe the most salient feature about quantum mechanics is that we can't predict the future with exactly the same initial state. Something different can happen every time you do the experiment over and over again, but you can predict the probability for any given final state. And in order to calculate that probability, you're supposed to sum up all these pictures and take the square of the answer at the end to get the probability. But anyway, so this is, again, in principle engineering. We've known how to do this for a long time, and it just looks complicated. And if you do it, it is complicated. Okay? So there's like 100 pages of very complicated looking algebra if you actually just do it from textbook ways of doing physics. Okay? So, and that's fine. Not every question has a simple answer, and part of the chauvinism of fundamental physics is to declare as interesting only those questions that have simple answers, and as engineering, those questions that don't. However, physics also has a wonderful way of rewarding morally good behavior. And people actually needed to do this calculation in order to, connect with the experimental program at colliders like the LHC. And a little over 30 years ago, they found something astonishing, that these hundreds and hundreds of pages of algebra, in some cases, actually collapsed to a single term. Okay? So this is completely nuts, that naively you would think, well, it's complicated. 2 things come in, 4 things go out. It can happen in zillions of ways. I got to add them all up. Of course it's complicated. I'm asking a complicated question, get a complicated answer. But when you actually do it and get to the bottom line, you find this sort of one-term formula. I'm not going to explain what these symbols mean now or maybe ever, but it should make you clear there's something going on. You see, Feynman's way of doing this physics makes the usual rules of space-time and quantum mechanics as manifest as possible. That's its raison d'etre. Okay, that's what made him justifiably famous. So you want to make the rules of space-time and quantum mechanics as manifest as possible. You'll get Feynman's pictures, and you will think that the answer looks like hundreds of pages of algebra, and yet it doesn't. It isn't. Okay? So there's some kind of new extraordinary structures that are lurking there, just hiding in plain sight under our noses. Not in some exotic speculative place, but in the behavior of completely conventional, ordinary physics. It's just that we're being invited to think about completely conventional, ordinary physics from a new point of view. And presumably from this point of view, the principles of space-time and quantum mechanics will not be the stars of the show. Some other ideas will be the stars of the show that will make the fact that these formulas are incredibly simple obvious. And perhaps if we understand what those principles are in a general enough setting, we'll begin to understand where space-time and quantum mechanics might actually come from. So that's the logic that's motivating this line of work. And again, there's lots of clues to this structure going back 30 years, 20 years, but there's a particular point of view and angle on it that's been pursued over the past decade or so that has begun to see the emergence of new structures in mathematics that seem to be deeply connected to these very basic physical questions. Again, I want to stress these things, they're not just relevant to the Large Hadron Collider, right? They happen all the time in the world around us when you look out the window, right? Essentially, everything that happens in the world is a concatenation over and over again of these basic elementary scattering processes happening over and over and over. So it's the most basic process in nature, and it's astonishing that the most basic process in nature seems to be governed by ridiculously complicated answers, which, however, have incredible simplicity and hidden structures underneath them. And what is it that makes it look complicated? Forcing it to look like it respects quantum mechanics and space-time. So what are we invited to do? Find some way of thinking about what the objects are from a different point of view. And so clearly, as I mentioned, there have to be some new physical and mathematical ideas involved. And the mathematical structures that are emerging are in very sort of interesting parts of mathematics that have not typically had any connection with physics, never mind connection with physics at such a basic level, in areas like combinatorics, number theory, and various aspects of algebraic geometry. And in various concrete examples, we can begin to see how the rules of space-time and quantum mechanics can actually come out of some more primitive structures. And so what I'm at least my own point of view about what's going on is that the string theorists have started telling us 20 years ago and are continuing to intensively study this sort of fascinating fact that quantum mechanical systems can in some cases give us space emergent from the strong quantum mechanical interactions of particles. But my own suspicion is that further in the future, we need to instead be looking like something like this. You see here, there's an asymmetry. Quantum mechanics is sort of on top, is king, and space and gravity and so on emerge from it. Whereas, at least my own thought is that there are some more abstract set of ideas and that we'll see quantum mechanics and space-time, not just emergent space, but space-time emerge together, joined at the hip inexorably. And one of the sociologically interesting things about it is that far-flung physicists and mathematicians have been brought together in a fruitful and active collaboration. Now, I think I have around 10 minutes. All right, 5. So I want to at least give you a flavor, and this is just meant to be a flavor of what some of these mathematical ideas look like. And to also give you a flavor of what some of the physical ideas are. So let's go back and talk about the interactions between gluons. And the very, very simplest interaction you could think of is when 3 gluons meet at a point in space-time. Not really 2, because that just is a gluon moving on a straight line. Okay, so that's no interaction at all. But the simplest interaction that we can have is 3 gluons meeting at a point in space-time. Now, I didn't tell you, but the gluons also are sort of spinning particles. So they're moving along at the speed of light, but they're either spinning in the direction of motion or opposite to the direction of motion. So that's the plus and the minus sign here. And it turns out that while those other amplitudes with 2 to 4 gluons and so on are very complicated, these very simplest amplitudes are incredibly simple. Again, I'm not explaining what these symbols mean, but just so you see that there's some extremely simple thing that goes into the very basic, most basic interactions that we were talking about. So where do all the complicated things happen? All the complicated things happen when we draw these pictures of Feynman, and in these pictures, in all the stuff that's going on in the inside, the particles that are moving around on the inside there, they're not real. They're what we call virtual particles. Even if you read sort of popular descriptions of physics, they're called virtual. And that's because they don't actually propagate a long place from one place to the other. In principle, from infinity on one side to infinity on, from minus infinity on one side to sort of plus infinity on the other. They propagate over finite distances, they're produced and absorbed. They're not real particles. They're sort of, as their name suggests, they're a convenient fiction that we introduce as sort of theoretical physicists to give a rational description of what happened inside here. But, you know, an experimentalist who just throws the particles in and sees them come out, they don't see all this stuff happen. It's a theorist who tells them, no, 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 what's going on in there is you made these virtual particles and you sum over all these ways that are happening. And in fact, it's exactly the existence of these virtual particles that's the origin of all this horrible complexity in these calculations. These sort of hundreds of pages of algebra are a consequence of demanding and thinking that all these virtual particles are in there. So there's something else that you could do. You could go back and say, forget about virtual particles. The physical idea is we're going to eliminate virtual particles. On the other hand, we want to somehow keep the idea that we're going to build more complicated interactions by piecing together simpler ones. But what we could do is take these exactly physical processes where every particle there is a physical particle, not a virtual particle, and we could see what happens when we glue them together. So these pictures are not Feynman's pictures. Everything here would correspond to sort of a non-virtual gluon, but we can just experiment and see what happens when we glue these building blocks together. And then we discover some very interesting things. So for instance, if you're talking about a process with 2 gluons in and 3 out, this single picture, where what you're gluing together are the real processes, that actually gives you the total answer for the process with 2 gluons in and 3 gluons out. That single picture, where everything here is physical, not virtual, this single picture is what we get instead of the 30 pages of algebra. If we do the 2 in, 4 out, that's a little more complicated, but it's this funny picture, plus 2 more that look just like it, just sort of cycling these indices forward by 2. So it's 3 terms that add up to the correct answer instead of 100 pages of algebra. So that's very interesting, that once we decide, we banish this notion of, the notion of virtual particle. If we only allow ourselves to glue things together in this physical way, then we find these extremely simple representations of the actual answer. But we also discover that the individual building blocks cannot be given a description as an actual space-time process. Okay, so these are not meeting at points in space-time. These are not sort of local processes in space-time. So we can write the answer in this incredibly simple way, but the individual pieces do not look like they come from local space-time physics, nor are they individually compatible with the principles of quantum mechanics. And yet, there's some kind of world of ideas that spits out these basic building blocks that doesn't care about space-time and quantum mechanics, but somehow manifests the simplicity of the answer. And also, after you play around with this for a while, you understand there's a huge array of different ways of expressing the answer in this form. And so you start to wonder, what sort of new world of ideas do these objects come from? And so that was the physical idea, to eliminate the notion of virtual particle. And now I want to give you a flavor of the kind of mathematical ideas that end up being behind where these things come from. And to do that, we're going to strip off almost all the complexity of the scattering of particles. Instead of thinking about the energies and the directions they're coming from, I'm going to imagine scattering them only by scattering their labels. So I have particles 1, 2, 3, 4, 5, let's say, coming in, and their scattering is just going to scatter around the labels. Okay, so it's 1, 2, 3, 4, 5, and I'm just going to scatter them, quote unquote, by turning it into 3, 5, 2, 1, 4. It's one of the most basic things that you could talk about in mathematics. It's a permutation. Okay? I just take 1, 2, 3, 4, 5, and I permute them. What in the world could permutations have to do with the scatterings of gluons, blah, blah, blah? Well, we'll see in just a second with a few pictures. In fact, there's an old relationship between this very basic notions in combinatorics, permutations and scattering, that goes by the following thing. So let me imagine just graphically denoting the permutation by writing 1, 2, 3, 4, 5 down here, and 1, 2, 3, 4, 5 up there, and I'm just going to draw a line for where everyone goes. So 1 goes to 4, 2 goes to 3, 3 goes to 1, and so on. Right? So I've just graphically denoted the permutation. Right? I haven't done anything. But all of a sudden, that looks like a scattering process. It looks like I have a bunch of particles in one dimension of space, 1, 2, 3, 4, 5, and they move up in time. So 2 and 3 are moving up in time. They hit each other. Then this hits 1. You see, this picture of this way of graphically representing a permutation also represents a picture of a scattering process in one dimension of space and one dimension of time. And in fact, there's a very beautiful and by now classic story in mathematical physics that connects permutations to scattering in one dimension of space in this way. But this is clearly very special, one dimension of space. We don't live in one dimension of space. And it's very important that the basic scattering processes here involve two particles in and two particles out. There's no creation or destruction of particles. And that's the most fundamental thing that we saw before. It was the basic interactions where three gluons meeting at a point. So two can create one, or one can create two. Okay, so, all right, but maybe around 15 years ago now, 17 years ago, mathematicians discovered another graphical way of presenting permutations. Okay? And it goes like this. You draw, if you want to, let's say, permute 1 to 3, 2 to 1, and 3 to 2, you don't draw 1, 2, 3 down here and 1, 2, 3 up there. You draw them around a big circle, and you put a little black dot in the middle. And the rule is, to see what happens, is you walk in to see where does like 1 go. You walk in from 1, and if you hit a black vertex, you make a right turn. Okay? So you see, if you do that, in this example, you get 1 to 3, 2 to 1, 3 to 2. You could get the opposite way to do the permutation by using a white vertex. Okay? And so then I can now glue them together in more interesting ways. And if you just follow your nose, left, right, as you hit white and black vertices, this also produces a permutation. 1 to 3, 2 to 4, 3 to 1, 4 to 2, and so on. Now, what's remarkable is that every permutation can be represented like this. Okay? So there is a reason, purely within combinatorics, another graphical way of representing the most basic scattering process imaginable, just permuting things. There's a graphical way of representing it by exactly the kind of pictures that we saw were associated with the most basic physical processes that we are talking about. Okay? So that just gives you a flavor of why combinatorics has to do with this subject. And I don't have any time to talk about the rest of the story in detail, but just to say that the sort of big picture is that there's a mathematical structure where if you give me the energies and the directions that the particles are coming from and their spins, whether they're spinning in or opposite to the direction of motion, you build a certain geometric shape associated with that. And the volume of that shape gives you the amplitude for the scattering process. And if you want to sort of calculate the volume, you might want to break up the shape into simple pieces. There are lots of different ways of breaking it up into simple pieces, like building a jigsaw puzzle or cutting this object up in different ways. And each one of these pieces is represented with one of these sort of physical-only processes that we talked about that were fundamentally associated with permutations. The pieces don't have a space-time or quantum mechanical interpretation, but the full volume does. And in a very precise sense, the rules of space-time and quantum mechanics arise as derivative notions from this more abstract mathematical structure. So that's really all I wanted to say about the kind of things that we've been seeing. Maybe I'll make one sort of technical comment and one general comment before ending. The technical comment is that what we've been seeing in these examples is not just that space-time can come out of more primitive principles, but it's really that the principles of space-time and quantum mechanics are tied together. They both come out of the same kind of more abstract underlying rubric. But the more general comment I want to make that I sometimes talk about in public talks is this has been, especially this last part of the talk, very abstract, very theoretical. What the heck could this possibly have to do with what anyone in the world might care about? And often when people in basic science are asked this question, we point back to famous examples from history. Famously, Michael Faraday was asked by some British politician, what good is the experiments he's doing in his lab? And he said, I don't know, sir, but one day you will tax it. Okay? And it ended up being true, but it ended up being true 50 years later. And quantum mechanics, when it was being developed by sort of 20 people studying seemingly abstruse questions, 50 years later led to amongst other things, the invention of the transistor that completely revolutionized everything about our daily life. So why does this happen over and over again? Is it an accident? You could say over and over again it's just an accident, and it won't keep happening. But I think there is a reason it keeps happening. And it's because in this part of science, we're asking very basic questions about things in the world that we take for granted around us. You know, 100 years ago, it was not obvious to people that the question, why is grass green and why is water wet, were good questions about the world. Right? They might have had random answers. But it turned out that the ordinary properties of completely ordinary, seemingly nothing exciting about it going on matter around us needed quantum mechanics in order to understand, and having control of what that matter looks like that was offered by this deep understanding that ultimately was a deep theoretical understanding that came from theoretical physics was what was eventually needed to harness this enormous magic that was hugely beyond the reach of any individual or even large collection of human beings. Today, I think the analogy is there's something that we take massively for granted about us, which is the very existence of the space and time around us. Okay? That's even more obviously something to take for granted that just exists, that there's nothing to do about. And I'm not guaranteeing that if we understand what space-time is more fundamentally, that in 100 or 200 years we'll have some major technological breakthrough. But I am guaranteeing that the only access we have to power and magic and mystery and awe that's vastly beyond the reach of any individual human being is out there in the universe. And the only way that we can access it is by studying it. Thank you very much.
Thank you very much. I'm glad that space-time is still working here, so you're here to answer questions. If not, everybody is totally flashed. Yes, please.
Hey, thanks for the great talk. I have a question about the emergence of space from quantum mechanics. So, as you nicely explained this in ADS CFT, there's this way where one dimension emerges from like a notion of scale on the boundary. So I was wondering whether you know of any concrete example, or whether you can think that any, especially with this slide in mind, whether you think that any concrete example can exist where more than one dimension emerges from hardwired quantum mechanics.
Well, since you already mentioned, since you're probably part of the cognoscenti already for at least part of this question, already in classic ADS-CFT, more than one dimension emerges. We normally say there's a sort of one holographic direction that emerges, but in classic ADS, there's a whole extra 5 dimensions that emerge as well. It's just not infinitely large. It can be very large, compact, sort of spherical spaces. So I don't think there's anything very deep about the number of dimensions that emerge, and there are examples where a large number of dimensions emerge. But the emergence of time is a totally different thing. So that's the real difference, and that's the real basic difference between the world in a box and our world.
Okay, I see a question in the back, sort of third or fourth row back there. Yes.
Hi, thanks for the great talk. So at the very end, when you were talking about how you are composing these scattering processes out of permutations, it reminded me of applied category theory, and especially when you mentioned the amplituhedron, I guess that. So am I correct in assuming that? And if so, could you maybe elaborate a bit more on that?
I should say that I think I'm not a mathematical physicist. I'm a normal physicist, I guess. I don't know what, I mean, I love math, but that's not the same thing. The fact that a bumpkin like me is driven into stuff like this is just an example of the power of physics and the power of these ideas out there. Is that they're out there. They have nothing to do with how crappy you are. They even take crappy old me and force you to follow your nose and get into this crazy mathematical territory. And I say all of this because even 6 months ago, if you said the word category theory to me, I would have laughed in your face and said it useless formal nonsense, and yet it's somehow turned into something very important in my intellectual life in the last six months or so. So I don't know the answer to your question, but it is a startling thing that mathematicians find structures that end up being of some some deep use to physicists. One of the interesting things about this subject, though, is that it's novel in the sense that, I mean, there are some examples like it in history before, but not as many as the more classic connection between physics and math. The more classic connection between physics and math is either math is 50 years ahead and it's all sitting there and the mathematicians moved on to something else, and then Einstein is like, oh, thank you, Riemann, for giving me differential geometry so I could use it for GR. Or similarly with group theory, mathematicians were 150 years ahead in that case. And more recently, in the past 30 or 40 years, quantum field theorists and string theorists have gotten intuition, physical intuition for objects, physical objects that make mathematical predictions that are astonishing to the mathematicians. But that's a case where, you know, it's a physicist in the lead, and they know all the right answers, and the mathematicians are desperately trying to catch up and understand. This is an interesting subject in that, for very mysterious reasons, the physicists and mathematicians are running into the same very large, strange animal around the same time. And so it's not that one group is ahead of the other, and so we're sort of talking to each other and have very different intuitions for what these beasts are about, but they're being gradually explored together. So it's not an example of the sort of category theory is all just sitting there and it just has to be applied. There are some particular aspects of categorical thinking that turn out to be very relevant, not for literally what I talked about, but for things in this neighborhood.
Okay, we can afford one more question, and I know there's a lot of brain power in this room. Yes, please. We have a question in the first row.
Right here. Oh, right.
Well, thank you again for the interesting talk. One simple question: which type of measurements you would wish to have? I mean, you have a collider picture on your T-shirt. You have shown some of these. So among everything we are measuring in the universe, on the small scale, on the large scale, on the low energy, high energy, on the vacuum, which one you would pick up to make some progress?
This is a very, very large question on which I have many interesting things to say. but I would say that, at least I think they're interesting. But I would say that, the quick answer is that I'm personally most interested in measurements at the extremes. So I'm interested in very high energy collisions, and I'm interested in cosmological observations on the largest possible scales. And what's truly amazing is that these two sets of ideas are related to each other, and not just sort of vaguely related, but actually very concretely, even technically related to each other. There's a sort of famous fact that to understand the early history of the universe, you see the universe is huge today, but it was expanding. So early on it's very small. It's very small, very hot, very high energy. So that's one reason why there's a connection between very high energy physics and the universe, because the early history of the universe had very high energy collisions in it. But there are actually deeper and more subtle reasons. If you go way back to at least to a picture of the very early universe that many people believe and has lots of indirect experimental evidence called inflation, there's a remarkable picture of this early inflationary period where the universe was expanding in size, doubling in size, you know, every 10 to the minus 36 seconds or something like that. And that grew as teeny tiny initial speck into the entire observable universe that we see. And one of the most amazing stories in science in the 21st century, I think, is that there's a picture that very tiny quantum mechanical fluctuations in the early universe are stretched out by this inflationary epoch to give us hotter and colder spots on the sky that eventually turn into places with more and less mass, that eventually turn into places with denser and less dense matter, that eventually turn into you and I. Okay, so all the clumping and all the structure that we see around us comes from these quantum mechanical fluctuations very early on. The mathematics and the physics and the mathematics that involved in those quantum mechanical fluctuations in the vacuum are technically and conceptually very, very similar to those of particle scattering processes. And so that's why questions about very high energy scattering, as well as questions about observations on the sky at enormously large distances, turn out to be very closely connected to each other. But anyway, that's kind of a theorist fact. Observationally, as far as learning about the universe, nothing beats, in my mind, going to the extremes and seeing what's there. And it takes a long time. And, you know, but people have been doing this for thousands of years. We'll be doing it for thousands of years to come. Maybe machines will be doing it at some point. But we can't stop doing it.
Okay, thank you very much for this great talk, for answering the questions. Now we have a break and time to discuss all the food for thought that you gave us. And please be back at 8:15 for the second round here, and we'll have the physicist talk with the sociologist about the consequences of all that. I'm sure you're looking forward to it.